Hello, in the last lecture I have shown how to reduce the number of states of a DFA using mark and reduce procedure. Mark and reduce procedure is basically used in case of transition diagram. Now, if a transition table is given to you, how to reduce that machine, that we will show you in this lecture, and that procedure is called method of closed partitioning. So, method of closed partitioning is basically what they do, that they try to find out in this procedure, they try to find out the different partitions. Suppose if I say that partition P2 consists of some states within a bracket, means that those states will always behave like same if I give an input sequence of length 2. In this way, our main goal is to find out the states which are within the same bracket and with infinite with p infinity. That means, if I give an input of length infinity, they will always show you the same output. So, if we can find out these types of set of states, means that they will always behave like same, and instead of taking multiple states, I can take a single states, and in this way we will reduce the number of states. Now, it is a briefing of the entire procedure that I have told. So, to know it elaborately, we need to know two things, that is, one is called k distinguishable and k equivalent states. So, what is k distinguishable states? So, two states S I and S j are said to be k distinguishable if and only if there exists at least one finite input sequence that when applied to machine M, input sequence, sorry, it should be of length k, when applied to a machine M, will produce different output sequence. So, and similarly for what is k equivalence? The same, the definition will be same, only changes that we have to make is that k equivalence of states. Two states S I and S j of a machine M are said to be k equivalent if and only if there exist one finite input sequence that when applied to M sequence of length k when applied to M produces same output sequence. So, let us see an example, then it will be clear to us. So, let us consider a state table. This is a state table. This one is my present state, and here I will find out next state and output z. This is next state, and this one is output z for the input x equal to 0 and x equal to 1. Now, my present states are suppose A, B, C, D, E, F. Now, outputs are E, 0, D, 1. Okay. So, this is my state table. So, whatever state diagram we have seen earlier, all the state diagram can be converted to a equivalent state table. Now, let us consider a set of states over here. Suppose I am considering a set of states A and B, and consider any arbitrary input that we are going to apply on this particular set A and B. Suppose I am applying 0, 1, 0, 0, 1, 1, 0, any arbitrary input. There is no restriction, you can take your own input. Now, if I applied 0 to A, what will happen? The output will become 0 for A, and the output for B will become 0. Now, the state will get changed to E and F. Right. Now, in if I have to apply the next output, that is 1, that I have to apply it on E and F. Right. Now, in E and F, if I apply the output input 1, then E will produce the output 1 and F will produce the output 0, and their states will be, next states will be F and C. So, now look at this, after applying a single input input sequence of length 0, that case we are getting the same output for AB pair. Now, when we are applying an input sequence of length 2, that case we are getting the output different. So, we can say that this pair A and B are two distinguishable, because they are producing different output in input sequence length 2, and one equivalent, two distinguishable and one equivalent. Now, suppose consider another example. So, like AC, A and C for the same input sequence. So, in AC, if I give the input 0, I am getting the output 0 and 0, and the next state is for A is E and for C is also E. Now, next input that I will give, that is 1, that is that should be on E, and E is same is the next state for A and C both, right. Now, for E, if I give the input 1, then every time I will get the output 1 only, and the state will also be F in both the cases. Now, as both the states have converged to a single state E as the next state, so whatever input I give afterwards, they will always produce the same output. Now, can we say that this A and C is not only 2 equivalent, 3 equivalent, 4 equivalent, 5 equivalent, 6 equivalent, they are infinite equivalent also. So, I can consider this pair of states as an equivalent pair of states, and they will always behave like same under any condition, pair of states, and instead of taking A and C separately, I can take a single state, because they will always behave like same under any set of input. Now, this way actually we have to reduce the number of states in case of a method of close partitioning, that we will do. Now, first we will consider a concept that is called P0 partition. What is P0 partition? P0 partition means P0 partition consists of set of states under the same bracket that produces same output for input sequence of length 0. That means, if I give any input sequence that is of length 0, they will always produce the same output. Now, what do you mean by the input sequence of length 0? That means, I am not giving any input. If I do not give any input, then all the states will produce the same output. That means, they will remain in the same, that is my initial state. So, what should be there in my P0 partition? All the states must be there within the same bracket, right. So, P0 must contains all the states within the same bracket A, B, C, D, E, F. Now, what about P1? Similarly, as per the aligned with the definition of P0, P1 must consist all the states within the same bracket that must produces same output with under the input sequence of length 1. Now, if I give an input sequence of length 1, what are the different kinds of inputs that may be? In input sequence of length 1, there may be two kinds of input, one is 0 and another is 1. So, after giving 0 and 1, all the states must produce the same output. Now, look at this, A is producing when you are giving the input 0 and 1, A is producing 0 1, B is producing 0 0, C is producing 0 1, D is producing 0 0, E is producing 0 1, F is producing 0 0, right. Now, can I say that after giving an input sequence of length 1, that is 0 and 1, not AC, Yes, A, C and E, they are producing the same output, that is 0 1, and whereas B, D and F are producing same output, that is 0 0, right. Now, in P1 partition we should keep A, C, E in one partition and B, D, F in another partition, because they are producing the same output. Now, let us consider what will be there in P2. P2 means all the states must be in the same bracket, that will produce the same output under the input sequence of length 2. Now, how to find it? Now, to find the P2 partitions, what we have to do, that what are the partitions that we got in case of P1 partition, we have to write it separately, that is A, C, E, another is B, D, F. Now, what the next state they are producing at x equal to 1 and x equal to 0. Now, x equal to 0 and x equal to 1, A is producing E D, C is producing E B and E is producing C F. Refer to this table only. Now, similarly, for B D F, what the output next states they are producing at x equal to 0 and x equal to 1. B is producing F D, D is producing F B and F is producing B C, right. Now, look at this, at A C E, which are in the same partition in case of P1, they are producing output E E C at x equal to 0. Now, I have to check that whether E E C is in the same partition is in the same bracket in my previous partition. My previous partition is P1. Now, at P1, whether E E C is in the same bracket. If there is, yes, they are in the same bracket. If there is in the same bracket, then don't do anything. Next, try for x equal to 1. Now, at x equal to 1 also, they are producing the next state is D B F. Now, whether D B F they are in the same bracket in my previous partition, yes, they are in the same bracket. So, A C E will remain within the same partition for P2 also. Got it. Now, let us check for BDF. In case of BDF, x equal to 0, I am getting the next state as FFB. Now, whether FFB is in the same partition in case of within the same bracket in my previous partition, yes, they are in the same bracket BDF. Now, for x equal to 1, what the next state I am getting? DBC, whether they are in the same bracket in my previous partition? No, because DB is in one partition and C is in another partition, that is under ACE. So, we have to divide it along BD and F in my next partition. So, it should be divided along BD and F. I am repeating again, BD, why I have divided BD and F? Because at x equal to 1 I got the next state DBC, where DB is in the same bracket, that is under BDF, and C is in the same bracket under ACE. So, we have to divide it so that they should be within the same bracket in my previous partition also. In this way, I got P2 partition. In this way, I have to find out P3, what should be there in P3. So, I am writing P3 over here. Now, in P3 again, let us make a demarcation so that there should not be any problem, because I need this. So, in P3, let us check with again ACE. In ACE x equal to 0, I have EEC, whether EEC is in the same bracket in my previous partition, that is in P2. Yes, EEC is in the same bracket, that is ACE. Similarly, DBF, whether they are in the same partition in my same bracket in my previous partition. No. Now, BD is in the same bracket and F is in another bracket. So, we have to divide along BD and F. So, here I have to divide it along BD and F. If I divide it along BD and F, then it should be AC is in one partition and E should be in another partition. And now check for BD. In BD, for x equal to 0, I have the output FF, right? It is in the same partition. And for x equal to 1, I have BD in the same partition. So, BD will not be changed. Now, for F as is a single state, so I do not have to check for this one. Now, for P3 we got that AC is P3 AC is 3 equivalent, BD is 3 equivalent, E and F is the single state. So, there must be infinite equivalent. Now, check for P4. Now, for P4 again for AC, if you see AC, then for x equal to 0 we have next state E, and for x equal to 1 we have next state BD. All are in the same bracket in my previous partition, that is P3. So, AC will remain same, E should be in same. Now, for BD, for x equal to 0 I have F, which is in the same bracket in my previous partition, and DB, which is also in the same bracket in my previous partition. So, it will also not be changed. So, now see that for P3 we have 4 partition, for P4 also we have 4 partition. Now, in the same manner, if we do for P5, we will find out the same partition, P6 same partition, P7 up to P infinity we will get the same partition, that is AC, E, BD and F. Now, we can say that they are infinitely equivalent state, because AC whatever input sequence length I give, they will always produce the same output. Same case also happens for BD also. If I give an input sequence of length infinity, they will produce the same output. So, I can say that AC must be within the AC must be considered as a single state. AC must be considered as a single state. This one, E must be considered as a single state. BD must be considered as a single state, F must be considered as a single state. Now, what I will do that? Now, I will create the equivalent partition, equivalent reduced table. Now, I am considering AC as alpha, I am renaming it, E as beta, BD as gamma, F as delta, and create my equivalent reduced state table. Now, this one is my present state for x equal to 0 and x equal to 1. Next state and Z, we have to find it out for alpha, beta, gamma, delta. AC is alpha, E is beta, BD is gamma and F is delta, and this one is my reduced table. Okay. Now, what will happen if I give 0 to alpha? Alpha means AC. So, A as AC both are equivalent. So, check either for A or for C. Now, I am checking for A only. Now, if I give 0 to A, it is going to E0. It is giving me E0 basically. So, E is beta, right. So, I can give it as beta 0, and for x equal to 1, I am getting D1 and D is gamma. So, it should be gamma 1. And for E, it should be C and F. C is again in AC, so I can write it as for E it is C and F, right. So, C is alpha, so it should be alpha 0, and F is delta, so it should be delta 1. And for gamma means BD. Now, let us I am checking for B only. I am getting F0 and D0. F is delta, so it should be delta 0, and D is gamma, it should be gamma 0. Now, for f I am getting b 0 and c 0. Now, b is gamma 0 and c is alpha 0. So, this is my equivalent reduced state. Now, in the next lecture we will show you some more examples, so that you will be much more confident in this procedure.